This is track 6, Pad Pwn by Nils and Rafael.
Hello everyone, thanks for coming to our presentation today. In this presentation we'll be talking about the security research that we have performed in payment terminals. We'll share with you how much fun we have had looking at this technology. What we will cover, well, we'll have an introduction first. We'll see why we decided to look at payment terminals and the approach that we took for looking at these devices and finding software vulnerabilities. We'll look at the payment terminal ecosystem, and we'll see the different components that form the payment terminal ecosystem and how do they tie together. Then we'll move on to chip and pin and EMV. We won't go too much in detail on EMV, and we will just be focusing on the aspects that are relevant for this presentation. Then we'll describe in detail the approach that we took for testing EMV. We'll have 3 different case studies for 3 different widely used terminals currently. For these 3 case studies, we'll have a demo for each of them, so I hope you guys enjoy. And just at the end, we'll have a conclusion. We'll discuss the future work that we plan to do on this research, and we'll have some time for questions and answers. My name is Rafa. I work as a security consultant and security researcher for MWR Info Security in the UK. I've done some innovative research in the past on the areas of USB, finding and exploiting vulnerabilities in USB drivers, and also in smart card software, finding and exploiting vulnerabilities of software that handles input that come from the smart card itself.
Hi, my name is Niels. I'm heading the research at MWR. Some of you might have seen the exploits I've demonstrated at Pad Pwn 2009 and 2010. And since then, I've focused mostly on Android security research. Both Rafa and I give the Android security workshop as well.
So why research payment terminals? Well, we realized that Android exploiters wasn't as much money as we thought. No, seriously now. Payment terminals are widely used. Rarely you will go for dinner and pay with cash, or do shopping and pay with cash. People normally use their debit card or credit card. Personally, I even sometimes pay a single coffee with my card. They are also attractive because of the data that they handle, the transactions that they process, payment transactions, and they are very attractive for an attacker, primarily from a financial perspective. The payment authorization mechanism, from the point of view of a merchant or a retailer, the person that has to use the device, when he sees on the display payment successful, that retailer trusts that terminal as being a successful payment. Because they are more and more powerful and they have more functionality. And with more functionality, the attack surface increase. We'll see payment terminals that has wireless, Bluetooth, they can be administered remotely, they can render adverts, and all this helps to the attack surface of the device. And because it's the single point of failure for the merchant and the card holder that is using these devices for electronic payments. There have been previous attacks, and these have been focused on hardware mainly. We have seen terminal skimming, where the hardware is modified to gather this data. Some of these techniques are relatively advanced, where they gather information and then they send this information via wireless or Bluetooth to the attacker. A little bit more of a less elegant attack are attackers that actually replace entirely the device for a malicious device that is identical to the legitimate terminal itself. We have seen also more sophisticated attacks where a malicious developer or engineer actually manipulate the application or develop an application that gather information about the payment transactions. There is a very good or interesting paper from MasterCard titled Understanding Terminal Manipulation at the Point of Sale. And this talks a little bit about this type of attacks. Something that is very interesting is when it talks about what criminals do to gather information and how they go to internet auctions to actually purchase these payment terminals. So they can gather information on how do they work and the technology that they use. And so the attacks can be more targeted. In the same way, this paper also describes a little bit about how they will also target specific payment terminals that are used in a specific retailer shop. This is something very interesting that we found on the internet in a forum post from a freelancer. For those that cannot read it from the far, it's basically say it's asking for someone to do a job. The budget is between $3,000 and $5,000. We need someone who can modify a payment terminals so that it will record track 1, track 2, and ping for debit, credit card transaction, and credit card transaction. Need to print out receipt and need to have a menu for debit card and credit. If card with chip is entered, it should say error. Please swipe card. That's not dodgy at all, is it? So we can see that there is people out there already putting some intelligence on how to perform this type of attacks and actually look at how attacking these payment terminals. Software securities. Well, payment terminals are essentially a small computer. They run a payment terminal application to handle the payment transactions, and as any other computer that takes data and processes data and run applications, there are software vulnerabilities. The attack surface can be based on the hardware peripherals that are on the device, such as the magnetic stripe, chip and pin, the network communication, serial port, JTAG, setup menu, if the attacker has got access to physical access to the device itself. The research approach that we took was to see if it was possible to find software vulnerabilities in these payment terminals. The approach that we took was completely from a black box perspective. Only using public available information that is available to anyone on the internet. Although it would have been very useful to have access to the SDK of some of these terminals, this would also put us under an NDA, and we wouldn't be able to share this information with you today, guys. For this research, we purchased payment terminals mainly from eBay and other providers, which would rather prefer to meet up in a car park, and they would only accept cash. Using second-hand terminals from eBay is very interesting because in the majority that we have purchased, they were already set up for payments. They have a payment application installed, and they were ready to go. So anyone up for a refund? So they were configured. Basically, what is been happening is that it's relatively easy to get these terminals from the internet and relatively cheap, mainly because with the recession and a lot of retailer companies going into administration, we have a situation where these terminals are being treated as asset, which people just remove them from the shop when they go into administration and they just sell it. And there doesn't seem to be a control where these terminals are wiped before they go on auctions. This picture here is our lab. As you can see, there is different type of terminals from different vendors with different functionality. Some of them are chip and pin, others are signature-based payment terminals. And this picture actually reflects very well the current share market of payment terminals in the UK. The common setups that we have seen are as follows. We've seen dumb terminals that are connected to a POS system, being the POS system the PC that the person in the shop actually perform the payment transactions. These dumb terminals are actually very simple, and there's very little functionality within them. Most of the core payment functionality is happening in the POS. The POS sends commands to the terminal, and the terminal it basically acts as a interface for the user to enter the card. We've seen other type of terminals that are more powerful, and more of the core functionality is happening within the terminal itself, where they will have a payment application running that will handle the payment transactions. These payment applications can come from the vendor, third parties that have access to the SDK and they develop applications, or they are slightly modified vendor applications with the company logo or the welcome message. The way these terminals connect, and we've seen they can connect to internal systems, or they can connect to third-party providers going through the internet. So this is the payment terminal ecosystem where the different parties that handle payment terminals live. We have the manufacturer who design and manufacture the payment terminals. The manufacturers will provide the terminals to the acquirer. The acquirer acts as a third-party company who sells services to the retailer, such as setting up the terminal, personalizing the payment applications, doing any general maintenance service that are required, and the retailer is actually the consumer of those payment terminals. The ones that are going to be using these terminals to take payment transactions. The manufacturer also provide the SDK and the required development tools for the developer to develop the application and sign the applications. The developer will develop applications for the acquirer and for the retailer. We've seen in cases where actually the manufacturer can deal straight away with the retailer and provide all these services in one.
One particular focus of our research was chip and PIN payments, so where a smart card is used to make the payment. Some of you might not have come across that, especially if you're from the US, so we'll give a quick introduction of what that is. So chip and PIN payments are a major improvement over magstripe payments. It's very widely implemented in Europe. In the UK, for example, every single payment will be a chip and PIN payment unless you have a credit card from the US or from other countries that do chip and PIN. Basically, the payments are split up between offline and online payments. For an offline payment, the payment terminal itself will verify the authenticity of the card, and the user will verify the PIN against the card. And with online payments, the terminal will connect back to the bank or to the payment provider, and the payment provider will provide authorization for this payment. Compared to the magstripe, the chip allows for much better user authentication. It can, from one point of view, it can hold much more static data which authenticates the card, so much more information that that can be signed by the bank, for example, to say this is a valid card, or signed by the card issuer. And it also actively allows you to sign payments. So a card is now able to sign information which represent the payment by generating a so-called cryptogram. In the case of chip and PIN payments, the one side is a chip, the other side is a PIN. And the PIN number now replaces signature or IDs, which are commonly used in the US for authentication of cardholders. Quite interestingly, the US is also about to, or there are a lot of discussions around adapting chip and PIN and making chip and PIN payments mandatory, while it is already mandatory in a lot of other countries in the world. Really quick, just to understand the next few slides as well, an introduction into smart cards and how smart cards communicate with host systems such as payment terminals. When you insert a smart card into a payment terminal, it is powered up by the payment terminal, and as the first response to this powering up, the smart card will send an answer to reset to the device. And this answer to reset will hold information about the protocols that are spoken by the smart card, the type of smart card, and an ID for the type of smart card as well. And then the host or the payment terminal always sends commands. Commands are APUs, which is short for Application Protocol Data Units, and the host system will always send these APUs to the smart card. and the smart card only ever responds to requests sent by a host. So the smart card itself is never initiating any communication. The de facto standard for chip and PIN payments is EMV, which is short for Europay, MasterCard, and Visa. So this is a standard created by the most prominent card issuers. It is used mostly for credit and debit cards, but also for gift cards. So you might go into a shopping mall and might buy a gift card there, and that will use the same standard. Very interestingly, NFC payments very, very often use EMV as well as an underlying protocol for communicating between the NFC reader and the NFC smart card. There are some older implementations, specifically in the US, which use older protocols, but nowadays almost all of them use EMV for communication. And EMV defines aspects of this communication between the smart card and the payment terminal, such as multiple card applications. So theoretically, you can have one credit card which has a Visa application and a MasterCard application and some other payment applications on this card. And while making the payment, the terminal decides which of these so-called applications to select for making the payment. And it holds a lot of data which identifies the card and which gives the terminal more information about the card. This will include not the PIN, the primary account number. The PIN is not stored as data, obviously, in there. Expiry date, and then also information which specify what specific methods for cardholder verification are supported by the smart card and other things. And it also defines how pins are verified and several other aspects as well. And there's a very useful resource on the internet, which is emvlab.org, and that gives you a lot of information on how EMV works, what kind of tags are used to store the data, and what data is stored on these cards. For us, specifically interesting when we were doing this research were the EMV records. In this case, a payment terminal is issuing several read records commands against a smart card, and it responds with the EMV records, which are stored in a TLV data format. So you have tag length value, which we see in ASN1, for example, quite often. And parsing of these kind of data, which you have seen also in ASN1 fairly often, is quite error-prone, because you have the length specified and then a value which doesn't necessarily need to match the length, and so on. This is an example of how data can be stored on a card. It is so these data structures can also be nested. So we see a record template first, and then the expiry date, effective date, and the primary account number as well. So that's all stored in these records on the card. If you want to know more about how these payment terminals are implemented, how chip and PIN payments are often implemented, and a lot of information about EMV and the whole process of implementing EMV, that's a very good book to read up on this, Implementing Electronic Card Payment Systems by Christian Radu, and that was very helpful in our research as well. So the next thing we did was to test how these smart cards communicate with the payment terminals and to see how they communicate with the payment terminals in order to find issues in this communication. Our first approach was man-in-the-middle smart card communication. This device, some of you might have seen if you were or are into satellite TV hacking. It's a device which you plug into any smart card host device, and then you plug the smart card into this device and connect it with a serial port to your PC, and theoretically it should show you the communication. However, we found this to be very depending on the timing of the payment terminal and timing of the card. And we got it to work on some terminals with some cards, but it wasn't very reliable. There's another solution for that called the Smart Card Detective, which we weren't able to get hold on for this research, unfortunately. So we had to find another way of doing this. And what we decided to do is to implement a smart card which logs commands sent to the smart card by a payment terminal, and also is programmable by us to program it with with responses to respond to a payment terminal. We decided to go for a sequence of responses. So basically, you have two options here. You can say that you want the smart card to respond to specific requests in that way, which is not the best way of doing that we found for EMV, because you might have requests which, based on the current state of the card, result in different responses. So we decided to program it with a sequence, so a static sequence of responses. So answer to the first request with this response, answer to the second request with this response. And we found that if you use the same card against the payment terminal, that this sequence will always be the same. So that worked well for us. Just from a practical point of view, for the implementation, we use basic cards, which is basically basic programming on smart cards, which is kind of ugly, but much easier to set up than Java cards. Actually, in setting up a development environment, especially when working with multiple people on a project, for Java cards, which works for everyone, is probably impossible. So we decided to go for basic cards, which comes with a very well integrated development environment, which you can straight away install. And then you have to program basic, but it's still better than setting up Java card development environments. So basically what happens and how we manage to see the communication between a payment terminal using this smart card is as follows. We plug in our programmed basic card with our specific program which does the logging and which can hold a sequence of responses. We plug that into a payment terminal. It will then log all the commands sent to it by the payment terminal on the card. And in the next step, we plug it back into our PC. And to this PC, we have a valid card, so a valid credit card connected as well. And the PC will now replay all the requests it has seen from the payment terminal. It will replay them back to the valid card and store the responses it sees from the valid card back onto our basic card. And then we repeat the process until we don't get any new requests that are sent by the payment terminal, and this way then we can build a card which works against payment terminals, and which at least kind of clones the card. It won't clone the card up to a point where you can actually make payments with it, because there's some crypto magic happening as well. However, you can clone it so that you can get fairly deep down into the protocol and look at the protocol and look at what is happening in this communication. So and that's basically what we use to look at several payment terminals. In this presentation, we included 3 of our payment terminals that we have been looking at. So these payment terminals, as we said, we looked at a bunch of payment terminals, and our research was fairly goal-driven, so we wanted to find and exploit some software security vulnerabilities in these payment terminals. And these were the terminals where we first were able to get some progress, to get some understanding of how they work, and find vulnerabilities in them as well. All the vulnerabilities are currently with the vendors. And there's one of the vulnerabilities is patched already, which is quite impressive. In our presentation, we don't want to name and shame any vendors, specifically because we don't have a fair view. So we can't say we have tested all the payment terminals in the same manner, because we went for the first ones where we got lucky and found vulnerabilities. And because the vulnerabilities are not patched yet, and even though there's a patch for one vulnerability, it will take, I suppose it will take quite a while to patch these in every shop that is out there, so we won't include any vulnerability details either. So the first payment terminal is this one. You might have come across this terminal if you like to buy your coffee at your coffee shop around the corner on any corner here in the US. And this terminal is, so it's very widely used in the UK as well. It's used in the US. In the US, you would stripe your card. In the UK, you will use chip and pin on these terminals. It is actually often connected through Ethernet, so it has an Ethernet port on the back, a serial port, it has a built-in modem to talk through the phone line, and an integrated printer as well. The first thing that we were able to do, and if you follow us on Twitter, you will have seen this picture, was to trigger a stack-based buffer overflow through the network communication of these terminals. Fairly straightforward stack-based buffer overflow with a lot of control on our side. So we almost were able to get any characters in there, any lengths of data, basically the perfect situation for us. And that's one of the reasons why we focus on this terminal then. This stack-based buffer overflow we were then able to use by sending a lot of data in there. And so on this screen, what you see is only very limited information and that was all the debugging information that was available to us as well. So we didn't have a debugger running on the devices. We didn't have more registers than this or a more detailed bug report. The only thing that we had was a status register, program counter, link register, and the address that led to the crash. By sending in a lot of data, we made it to crash not while returning from the function, which had the stack buffer overflow in it, but instead crash at the end of the stack. And that gave us an idea where the stack is located on these devices, at which address range, which then allowed us to jump into the stack. You won't see any of the memory protections that are common in computer or mobile phone systems. So we were able to execute code now on this device. But we didn't have much information what code to execute. From this error log, we can make a good guess and say this is an ARM platform, which at least allowed us to guess what kind of instructions to execute. But we had to do very careful probing and manual memory dumping like you see here. So that is a partial dump of the stack on the system to give us ideas of where the binaries are located, where the heap is located, and so on, until we got up to a point where we were able to have enough information about the system, mostly done by manual dumping, to dump the memory back to us arbitrary memory regions through the Ethernet connections, through the TCP connections that already existed, because that's what we used to trigger the fault. And that finally allowed us to properly analyze the application. We got an idea how systems call on this custom operating system work. We have never seen any references to the specific operating system. For all that we know, it's custom to these systems. And it also allowed us to find more weaknesses in the systems. Some of them, so in this case, we have a third-party payment application running on there by a third-party payment provider. And in some cases, we found hard-coded passwords in the application. So you actually have a check for the password from the configuration file, for example, for the setup menu, and then a second check if that fails against the hard-coded value. And we also found other vulnerabilities, and we were able to find vulnerabilities in handling of chip and pin payments. So the question here is how we got the stack dump out of the device. So we were able to execute, so we had some information about memory layout, so we had the stack address already. And then by executing code and executing, so at the beginning you will just end up executing code like, if this address contains this value, then go into an endless loop, and we see the device getting stuck, or jump to the value of the address at that address, and we will get the error log showing you the content at this address. And then slowly you can progress. At some point, you get some code back, and that gives you an idea of how to print onto the screen. And then finally, we were able to use that to dump more data up to a point where we were able to dump that back through the TCP connection, and then we can basically read all the memory from the device. So the first chip and pin vulnerability that we found in here is, again, a fairly straightforward stack-based buffer overflow in the handling of EMB tags. So that's the records that we have seen previously. And it allows us for arbitrary code execution. Now, for the implementation of an exploit against the devices, a single response to an APDU request to the smart card won't be enough to hold all the data, especially not in this case where we will only be able to control 40 bytes really after triggering the crash. However, we were able to use these 40 bytes to do return-oriented programming to call the methods that request more data from the smart card in order to retrieve more data from the smart card, which then contained our second stage of the payload. And the second stage was, well, around 200 bytes of control data, and allowed us then to implement a shellcode which can almost load an arbitrary amount of data from the smart card into the memory, and then we are able to execute this as our final payload. And in the demonstration that we will show now, this payload is actually 870 bytes of ARM thumb instructions. And that will be our first demonstration. So this is the terminal you already have seen on the picture. Previously, I hope you can at least fairly well see the screen, but that should be fine. And in this case, we demonstrate how to use a malicious smart card. This is our malicious smart card. Does anyone recognize the game? Very good. So we start a payment process on the device. In this case, it tries to connect to the bank network. Obviously, we haven't connected these systems to a bank network, but this one is set up to accept offline payments as well, and that's what we will do now. So we start an offline payment. It will be a sale or anyone after a refund. We start a sale, enter an amount, and that would be what is happening in an actual shop. So the merchant will start the payment process, enter a reference number, and then the customer is asked to insert or swipe the card. This payment terminal was used in the UK, so we insert a chip and pin card, which is this specific card. And that will trigger the stack-based buffer overflow through the weaknesses in the smart card handling on this device. We'll insert the card, we'll read the data from the device, and then it starts the racing game on the device. And game over. And also quite interestingly, on the card printer, we see how it prints the score. In this case, 46. The record in the office is at 715, which is very impressive. Gameplay on these devices is actually quite good, and they are powerful enough to run these kind of games as well. To the presentation. So our first demonstration. That's what you see on the terminal, printing of the score, and the MWR Labs PinPad Racer game. And that's the card that was used to trigger this issue. So what have you seen here? We have code execution in the context of the payment application. We reported this issue to the vendor, and the vendor is currently working on a fix. Interestingly, okay, this was a game, but playing a game on these devices is not the only thing that you can do with this kind of vulnerabilities. We use this game to demonstrate that we have full control over the printer and the display on these devices. If you now wear a merchant and the display says that the payment has been approved in the same way as the actual application does, and it prints out a valid receipt, then you probably think that the payment got approved, but there won't be any money arriving in your bank account. We'll see some more practical payloads later on. So this one, what we demonstrated here was a weakness in the payment application that runs on the payment terminal. We will cover operating system in future work later on. So in the next case study will be presented by Rafa.
So this payment terminal here is a little bit more different to the one that Niels just presented. These are widely used in the US, where chip and pin is not established yet, where you use basically signature-based payments. They have a nice touch screen, full color, where you can actually use to sign your payment. They have a 32-bit ARM processor. They run embedded Linux. They also have VCBox installed, which, as you can imagine, is very, very useful. And these terminals, I would say, are more the ones that are more similar to a computer itself. The hardware peripherals add to the attack surface. Some of them have a smart card reader, SIM card reader, magnetic card reader for the signature payments. They can also have contactless payments if they require NFC hardware is plugged into it. They will have a USB port, Ethernet port, and RS-232. There's two interesting security features in this payment terminal. The first one is binary signing for the application, for the payment application. So to protect against payment application tampering for malicious purposes. Physical tamper protection mechanism, which is a pain if you drop the device on the floor. These payment terminals come with a built-in application from the vendor, which are used to manage the terminal when you have physical access to it. This built-in application also allows you to set up a lot of configuration settings, and also allows you to configure the device to be to be managed remotely. On top of that, we will have the payment application, which handles the payment transactions, and is what the user will be basically exposed to. There are very interesting functionality in this terminal. They render multimedia adverts, so when you are purchasing with these terminals, you can actually be seeing adverts with it. They have a remote administrative interface, so retailers that has 300 of these payment terminals can actually manage this device from a centralized location, and they can connect to the internet. If the device is set up in a local network, they won't, but if these devices need to connect to a remote interface that is on the internet, they will be able to connect to those devices. And the demo that we're going to be seeing. So, okay, so this is the payment terminal. As we can see, there is a, let me just set this up properly. This is the built-in application that the administrator will use to manage the devices. Here we can see the different functionality that is available. You can set up FTP. It looks very much like the functionality that you will find in a Linux system. You can set up debug functionality. You can enable Telnet. What we are going to be doing is restarting the device. And the demonstration that we are going to show here is how we can exploit weaknesses in the network communication between the device and the remote administrative server that these devices connect to. So these devices actually act as a client. When they require administrative functions, they will attempt to connect to the remote server. What we are doing here for the purpose of the demo is rebooting the device. The user or the customer in the shop would actually not be seeing this. They will be exposed with the payment application but just to demonstrate that the communication is happening at reboot and can be also set up in periodic times to connect to the administrative server. We are going through this interface. Essentially, these weaknesses in the network communication could allow an attacker to spoof the remote server and launch an attack to the payment terminal itself. This is basically using functionality available on the built-in application. So it takes a little bit of time to boot up. I was expecting that. So it's almost there. So now we can see that the terminal is booting up. And now what it's going to be trying to do is to connect to the remote administrative server. So what we do from here is to impersonate the remote server. We have our malicious script that we can run. We specify the IP address of the client, the terminal, our IP address. and we launch the attack. Now the impersonation is happening, and we'll be launching our malicious application into the terminal.
So your question was whether it's a signature, digital signature is required for the application that run on these devices. For legitimate applications, it is. If you decide not to go through the normal startup process of application and start directly from the underlying operating system, and this signature is not enforced.
What our payload has also done is to enable telnet on the remote device and change the root password of the device. So we can do that.
And luckily that allows us to stop that demo as well.
Yeah. So what we have seen in this demo is a full system compromise. We have been able to run our unassigned application with the access that we have had to the device. We have changed the root password on the device, and also enabled telnet, which allow us to connect remotely.
And that leads us to our third and last demonstration on another payment terminal. And this is the specific payment terminal, very popular in the UK. I've seen it in the US as well, and has similar sorts of connectivity, Ethernet port, serial port, and so on. It runs the vendor software, however, a slight modification of the vendor software by a payment provider. It uses the same custom operating system, maybe a newer version of that, as the terminal in our first demonstration, which actually helped quite a lot because by now we understand that operating system fairly well. The same application is used on multiple devices, so it's not specific to this device, the demonstration. It is specific to the payment application used on these devices. And when we were looking at finding flaws in the chip and pin parsing, we noted that the code quality for parsing the EMV protocol was considerably better than on the first terminal that we were looking at. Still, we were able to find vulnerabilities, and those vulnerabilities were deeper down in the protocol, and they weren't as straightforward to find or exploit as the previous vulnerabilities. Interestingly, we again found, so first of all, on almost all of the terminals that we bought off eBay, we found that the default passwords are not changed by the people that are using these terminals, which is quite shocking. But then also there are hard-coded passwords. In this case, there is the so-called super mega password, which can be disabled in the configuration files, but wasn't disabled in any of the cases that we have seen. And that will allow you to get around any password prompt on the device. So that's our third demonstration then. Bear with me a second to get that up. We've got a lot of reflection here. So I think that works fairly well. The stripe of tape you see on there is because this for this demonstration, we will use an actual credit card, and I really would prefer if not all of you have my credit card number, or at least the number for this specific card. So what we do in this presentation is we have our first card, which looks like this. So that is Tinkerbell, and Tinkerbell will go ahead and put the pixie dust into the device. The pixie dust in this case being some kind of backdoor which modifies the payment application in a way that after this pixie dust has been put into the device, it will record all the credit card numbers and PIN numbers that are put into the device after this. So again, we start a payment process by inserting the card. And from the merchant's point of view, the payment process goes ahead as usual. They will put in a value for the transaction, and then it displays card error. A criminal probably now would go ahead and say, oh, there must be something wrong with my credit card. Can I pay by cash instead, and then leave the shop. At this point, our malicious code is on the device, and it will hook any payments that will be happening on the device after this. So we can now go ahead with a valid credit card, which is this one, and make a payment. So the next customer comes into the shop and uses the same device to make a payment on the device, and that payment will go through as it normally would. Merchant is asked for the amount of the payment, puts that in, and then the cardholder is asked to put in a PIN. Obviously, they will shield the PIN pad and hit enter. And now it tries to connect to a bank. In this case, it would use the modem to connect to a bank, which is not working because it's not connected to a phone line. It will have several attempts of that and then decline the payment because we weren't able to verify the cardholder. If this device would be connected to a bank, then the payment would go through as it would normally. And now several other payments can happen. I'll better keep this receipt because it has my card number on it as well. So several payments will happen throughout the day, and all of these payments will be locked. And now the criminal, at the end of the day, comes back with a second smart card, which is Winnie the Pooh retrieving the honey from the payment terminal. The honey, in this case, being credit card numbers and PIN numbers. So Winnie the Pooh goes ahead, makes a payment on the device. And this includes a small demonstration as well, because we can now put in the value for the payment. And because we have control over the payment terminal, it did authorize the payment without asking us even for a PIN. So you see an auth code there, and also it has printed a valid receipt, which you see here. So no cardholder verification was required, and the payment has been approved so this would usually say MasterCard, and the card number probably shouldn't have 31337 in it. So from the point of view of the merchant, this payment has been approved. More interestingly for the criminal is not that they were able to acquire goods for £10 that, without paying for it. More interestingly is that all the credit card numbers and PIN numbers that have been used throughout the day on this terminal have been locked to the Winnie the Pooh card. So what we do next is the criminal will go to their laptop and execute the cash-in script with _hide so that I don't have to show you my credit card number. So that will X out some digits of the credit card and also X out most of the PIN number. Criminal will go ahead, insert the payment card, the malicious second card into the card reader, and then execute the script. And that is the locked credit card number and the PIN, scrambled in this case, retrieved back from the payment terminal. So our third demo. Again, Tinkerbell for infecting the device, and we need a proof for retrieving the the credit card numbers and the PIN numbers. Again, code execution in the context of a payment application. We have demonstrated what else we can do with this kind of code execution. We can approve payments, and we can also modify the terminal so it records credit card numbers and PIN numbers. This vulnerability was reported to the vendor at the beginning of July after we found it, and they already have a patch for this issue. That's less than 3 weeks to get the patch for the issue out, which is really quite impressive, especially with vendors of embedded hardware. We have seen far worse than that. Unfortunately, it will take some time for all the shops and merchants to adapt this patch, and also for the new software version to go through the verification or certification processes. Right, what else is there to do? There was a mention of the operating system and security of the operating system before. So from what we know, it's completely custom built. There might be privilege escalation vulnerabilities. You can maybe exploit some of the system calls, something very interesting to look into. Firmware updates for the operating system itself, they are signed and encrypted, at least to our knowledge encrypted. So by looking further into the operating system, we might get an idea of, and we might be able to verify the signature checks and encryption. There's a lot of other code in there which is custom to this terminal. We have a custom Wi-Fi stack, Bluetooth stack, and the network stack is customly written and usually implemented in user mode as well. There are a lot of other payloads that we can play with, properly approving payments so that the merchant will think that this payment was approved using a PIN and a valid card without it actually being a valid card. And also, because all of these devices implement signature checks, currently our payloads are not persistent on the device. On reboot, these payloads will get lost from the device, which is, from a forensics point of view, great, but maybe not if you want to have large-scale attacks against these systems. So there are some ideas around how we might be able to achieve persistence on the devices, for example, modifying the configuration files because they are not signed, and if we trigger issues in the parsing of the configuration files, then we might be able to gain persistence on these devices as well. And then also looking into NFC would be quite interesting. As I said before, most of the NFC payments are made using EMV, the EMV standard as well, so similar issues, or maybe even the same issues might work against these devices. Very quick conclusion. There's a lot of trust into these payment terminals. The merchants trust them to tell them whether the payment was legitimate, and cardholders trust them with their card details and PIN numbers. They don't have another option than doing so. We have seen a lot of cases where the default passwords were not changed. Some of them had hard-coded passwords additionally. And we have seen a lot of effort put into the physical security against skimming and so on these devices. It would be good to see a similar effort for the software security as well. And finally, we demonstrated how memory corruptions vulnerability in the handling of user input, like chip and PIN cards, can be used to inject code and run code on these devices. And we have seen some payloads which allow us to exploit that. Any questions? Yeah? Can you turn off? We haven't looked into the storage of keys. I would assume they are securely hidden away from the applications. But we haven't looked into that at all. Yeah. There's another one. So, sorry, I can't hear you. My current implementation, but that is only because I was lazy, will allow you to store something like 20, 30 card payments. My smart card itself has a storage of 60K. I need 8 bytes to store the card number, and currently another 4 bytes to store the PIN number, so you can make your own calculations how many that would be. Any other questions? Yeah, so this was a comment around the software updates and how long it will take for them to actually get to the merchants. Yeah, so, and that it might not happen at all. But we have seen cases like in the first demonstration where an update channel through the internet exists by the payment provider. So that might be an opportunity to get patches more quickly to their payment terminals as well. Any more? Yes? So with all of the terminals we have been looking at, you can exchange the application if you have the developer key that is set up on the devices. On some of them we have seen that happening through an internet connection, so the same connection to the payment provider that is used to process the payments can also be used to update the devices. It is very dependent on the terminal that you're looking at. Any more questions? Last one. Okay, this question was around whether we were able to make the terminal accept offline payments even though it should do an online verification or is configured to do so. With the kind of access that we have, it's more about what you display on the screen. So we weren't able to approve any payments in the back-end systems at all. And no money will eventually make it to the merchant either. However, what we were able to do is make the merchant think that a payment has been approved. And that you can do with whatever payment you want, because we control the screen and the printer, and we can print that this was an online payment or make it appear that it is connecting to a bank while it isn't. Theoretically, you would probably be able to do so. We haven't attempted that. Any more questions? Thank you.